Welcome. In this video, we will continue our discussion of section 2.1, the beginning of mathematical proofs. In the first video, we looked at parts 1 and 2, a very first proof, and a few more examples. In this video, we'll look at a bad proof, some more practice, and then this idea of proving the contrapositive. Let's go. To begin, a bad proof. I will give you a proof that has an error at some point and see if you can identify the error. So here's the proposition. The result of summing an odd integer with an even integer is an odd integer. So no variables are given, and it's not really even written in if-then format, so I need to do that myself. Let odd integer x and even integer y be given. Since x is odd, x equals 2k plus 1 for some integer k. Since y is even, y equals 2k for some integer k. Then x plus y equals 2k plus 1 plus 2k equals 4k plus 1 equals 2 times 2k plus 1. Since 2k is an integer, x plus y is indeed odd. So where is the error? End of proof, maybe? Pause the video if you don't see it and take a little bit of time, but when you see the error, you can unpause the video. And the error is in this assignment of k. Never use the same variable to stand for two potentially different quantities. In the proposition, this odd and even integer should be any odd and even integer. Odd integer x, even integer y. But if I use the same variable twice, this k, then my x is an arbitrary odd integer, but that y is just one number less than x. X and y should be able to be anything as long as x is odd and y is even. But by using the same k, I'm making them only one apart, and I've lost the arbitrariness that I desire. Alright, moving on. Here's a little bit more practice. The aspect of these claims that I want you to think about is the fact that they are not written in if-then format. So you will need to think about it as an if-then statement and come up with your own variable assignments. Give these a try, and when you are ready, unpause the video and I will go through these two proofs. Alright, let's see how you did. Number 1. The product of any integer with an even integer is an even integer. Let x be an integer, and let n be an even integer. Since n is even, n equals 2k for some k in my set of integers. Oh, and by the way, I'm getting a little creative here. I'm using a lowercase k instead of my usual uppercase k. It really doesn't matter. Observe that xn equals x times the quantity 2k, which is the same as 2 times xk. And since xk is an integer, xn is even. This could be the end of the proof right here, because after all, my goal was to show that the product of any integer with an even integer is an even integer, and that's what I did. I set up my x and my n, I found the product, and I found that the product was even. But sometimes it's nice in a proof just to put one last sentence at the very end that reiterates the claim. So just in case you weren't aware, dear skeptical reader, what we just showed was the product of an arbitrary integer with an even integer is even. Just to hammer home the point one more time. Use sentence punctuation. Look how I have periods at the end of my sentences. Even at the end of a mathematical equation, it gets a period. And it's good practice. It's more tradition than a strict rule. But start your sentences with words, not symbols. See how I have let, since, observe, that is. So start your sentences with something English. The second proof. The sum of any two even integers is an even integer. Let m and n be even integers. Since m is even, m equals 2k for some integer k. Since n is even, n equals 2l for some integer l. Here's another rule that if you want to use the lowercase l as a variable, do not use a print l. Please use a cursive l. Thus, m plus n equals 2k plus l, which is 2 times the quantity k plus l. Since k plus l is an integer, m plus n is even. And then just to bring home the point, what do we really show? Thus, the sum of any two even integers is even. A couple more points on style. So, as I said before, we're thinking about these things as sentences. Notice that the equals sign acts as a verb in the sentence. Read this. Since m is even, m equals 2k for some k in my set of integers. So treat your equals sign as a verb when you're writing. Also, we're using these helping words to help us along. And it can get a little bit boring after a while if you're always saying since, thus. There's lots of things that you can say in place of thus. You can say hence, you can say therefore, or it follows. How about even this implies that? So there you go. There's some ideas to help you spice up your proof writing. Proving the contrapositive. It's a little bit surprising, but sometimes it is easier to prove the contrapositive of a claim than it is to prove the original claim. This seems a little surprising to me because, after all, the original claim and its contrapositive are exactly logically the same. They mean exactly the same thing, so why should one be easier to prove? But it is. Can't tell you why. Okay, here are two examples of claims where it's easier to prove their contrapositives. So first of all, can you state the contrapositives of these two claims? Number one, if n squared is even, then n is even. The contrapositive of that would be if n is odd, then n squared is odd. And just a quick note, I'm in the world of integers. The only numbers I care about at this point are integers. Now it's true that if I was thinking about all real numbers, then not even is not exactly the same thing as odd. But for us, for these proofs, we're in the world of integers. So for us, let us agree that as far as integers are concerned, not being even is the same as being odd. So then how would you state number two? The contrapositive of number two says if m and n are odd, then mn is odd. Pause the video, give these things a try, prove the contrapositives, and when you're ready to see the proof, you can unpause the video. Okay, in this case, I will just put up the proofs in condensed form, so you can read those and check your work, and read through those and see if you agree that they look okay. One point I will make is that it's kind of curious that claim number one is actually a special case of claim number two. Did you notice that? Look at that. Look at 2. If mn is even, then m or n is even. Well, what if m actually equals n? Say, if m equals n, then claim number 1 follows. Because mn then would be n squared, and then that implies that either n or n is even. Oh yeah, look at that. So if we had wanted to be very clever, we could have proven claim number 2 first, and then said, oh yeah, when I go to prove claim number 1, say, well, claim number 1 is really just a special case of claim number 2, and we're done with the proof. I wouldn't even have to go through all that stuff. Okay, I want to end this video with 2 more claims that are maybe a little more challenging. And they give us an excuse also to look at a couple more definitions. So here's the definition. An integer n is a perfect square if n equals m squared for some integer m. So here are the examples of the first few perfect squares. And a similar definition works for perfect cube or perfect fourth power and so on. And this second definition, maybe which is a little more important, an integer p greater than 1 is prime if the only positive integer factors of p are 1 and p. And so here are the first few prime numbers. When we look at prime numbers in proofs, very often there's a trick we use based on this definition. And here's how it works. So suppose I have the number 13, which is prime. Suppose I write 13 as a product of 2 positive integers a times b. What do you know about the integers a and b? Well, it follows from this definition that either A equals 1 or B equals 1. One of those numbers has to be a 1, and the other number has to be a 13. There's no other way that I can write a factorization. We don't usually think of factoring primes, but this is exactly what happens. You can factor a prime, but one of those factors is always going to be 1. Okay, here are the two slightly more challenging statements to prove. One is definitely doable, so give that a try and see if you can form a proof for that. 2 is a bit more challenging. Think about it for a little bit, see if you can find a proof, but I will prove that at the end here. Okay, so as we often do, pause the video, give those a try, and when you're ready, the next 2 slides will step through the proofs of those 2 statements. Alright, let's take a look at the proofs. So 1, every even perfect square is divisible by 4. Let n be an even perfect square. Then, by definition, n equals k squared for some integer k. Since k squared is even, k is even. This is where I'm drawing on a previous result. Do you remember that from a few slides back? So, k is 2m for some integer m. So here we go, n equals k squared equals 2m squared equals 4 times m squared. And since m squared is an integer, this tells us n is divisible by 4, and it's the end of a proof. This is a technique that's used all the time in mathematics. We rarely prove statements from the ground up. Statements build on each other. I prove one thing, and then I use that to prove another thing later on, and I use 3 things that are known, and I prove something else. So we are laying a foundation now, and we're going to just keep building and building and building on this foundation. Let's take a look at the last problem. Here is the statement. 3 is the only prime number that precedes a perfect square. Now, pause for just a second, and let's think about the statement of this claim. This is actually kind of cool, and this is a much bigger, much more interesting claim than anything we've seen up to this point. You think about all the perfect squares that are out there. There's an infinite list of perfect squares. But with all those perfect squares, is there no prime number in front of any of those except for the number 3? That's a little surprising. So this is what I like in mathematics. We are actually finding a mathematical truth with this proof. We're not just getting some answer like 17.3. Okay, so let's prove this mathematical truth. 3 is the only prime number that precedes a perfect square. So as an if-then, I might say, if p is prime and p plus 1 is a perfect square, then p equals 3. Let a prime p be given such that p plus 1 is a perfect square. Since p plus 1 is a perfect square, p plus 1 equals m squared for some integer m. Let n be the absolute value of m. The reason I do this is because this m that I chose initially, it could be positive or negative. I want to be sure that I'm really only dealing with the positive version of that. Since p plus 1 equals n squared, and p is greater than or equal to 2, we find that n squared is greater than or equal to 3. Thus, n is greater than 1. So, right, n squared being greater than or equal to 3, I could take the square root of both sides, and I have the positive n, and it really is a positive number. So, square root of 3 is about 1.7, but these n's are integers, so n has to be greater than 1. Thus, p equals n squared minus 1. Do you see how I took the equation above and I just subtracted 1 from both sides? P equals n squared minus 1. And here's where the magic happens. N squared minus 1 can be factored. It's the difference of 2 squares. It's n minus 1 times n plus 1. And both factors are positive. This is why I wanted my n to be a positive number. In fact, n greater than 1. So look at this. I've taken a prime number and I have factored the prime number. What do you think is going to happen next? Since p is prime, one factor is 1 and the other factor is p. Now, do you think you know which factor has to be 1 and which factor has to be p? Well, 1 is less than p, and this first factor is less than the second factor, so we can conclude that the n minus 1 is 1. Now, look at that, n minus 1 equals 1. That tells me that n equals 2. And if n equals 2, I can come back to here. If n equals 2, then it follows that p, which is n squared minus 1, actually equals 3. Hey, look at that! And that's the proof. We just completed it. So this proof was definitely a little more tricky than some of the others, but even more fascinating and even more impactful. This is crazy. By the way, maybe you can do this now that you've seen this proof. It turns out that 7 is the only prime that precedes a perfect cube. So maybe think about how to prove that. And once again, the power of proof. This is great. This is why I like mathematics. And this is why I like proof writing in general, that we're really discovering and establishing mathematical proofs that were proofs of statements that were true since the beginning of time and will always continue to be true. It is a fact that 3 is the only prime number that precedes a perfect square, and it's just kind of cool that we can prove something like that. All right, and this ends section 2.1 on our introduction to proof writing.